Hello, for data communications and network one class today, Ajahn Dusnai will talk about protocols and we will use an example of the data link layer protocols, okay, which is the layer 2 of OSI model. Okay, if you remember, we have 7 layer OSI, right? Okay, and we have like physical layer, and then data link layer, and so on. Okay, 7 layer. Okay, so this is layer 1, layer 2. Okay, so data link is in the layer 2. Now what is protocols? Okay, protocol is something that is needed for the two sides, okay, for the sender and the receiver to be able to communicate with each other so that they understand what is going on. Okay, if you think about it, okay, what is actually sending is in the layer 2, what is actually sending is like 0 1, something like this. Okay, only binaries. Okay, and then this is sent. Okay, usually we modulate. Okay, and then we modulate into signal. Okay, and then we send to channels, to the channels, and then we receive like signal with noise, whatever, and then we demod. Okay, and then we get this, and this may have some errors. Okay, okay, in terms of signals that we actually sending into the air, into the wire. Okay, this is the physical layer, or layer 1. Okay, layer 1 of OSI. Okay, we actually sending signals. Okay, but we separate, if you remember the OSI model, we separate the works, okay, between layers. So in terms of data link layer, we look at it as binary sequence. So this is data link layer, binary sequence, okay, which is layer 2. Okay, and we have to be able to understand what the bit sequence mean. Okay, what each bit in the sequence mean, right? Like in the English, we will have like this is subject, this is verb, this is object, something like that. Okay, so that you understand the position or the location of each alphabet. Okay, so this is like location of the bits. Okay, will tell you what it means. Okay, so let's look at the more details. Okay, second layer of OSI model. Now, this is on the side, okay, that the most common protocol that you may have heard is Ethernet. Ethernet is used in LAN, local area network. So we will not talk about it here. We will talk about it when we are talking about the topic of LAN, okay. But this is also a data link layer, okay. What we will talk about in this slide and in the next slide is called High Level Data Link Control Protocol, or HDLC. Okay, this is very old protocol, but it's very important. It is basis for other protocols. Okay, I'm trying to find a very new like protocol, like update protocol to teach. Okay, but I find that they all refer back to this one. Okay, so this is kind of the fundamental of understanding the data link layer protocol. So I will teach this also. And when you go to work, okay, after you are learning like the concept of the data link layer protocols, they also I will talk about Ethernet when we talk about LAN, right? And I will talk about internet protocol that we are sending in the networks, okay, internetworking. So you will study like TCP/IP protocol. So you study some protocols, okay, and they have some difference and some similarities, okay. But when you go out to work, you will have to learn the the actual protocol that your company is using or the standard at that time is using, okay? But you will be able to understand them because really if you understand the concept of some important protocols, okay, then you can apply it, okay, to understand the the one that you have to use later on, okay? So HDLC is a point-to-point or point-to-multipoint link, okay, protocols, okay, and so this is standard 2002, so it's quite old, okay? So point-to-point is this, point-to-multipoint is this, right? Okay, now HDLC, there are some basic characteristics, okay? It is for two-way communications. When we talked about the flow control and error control, those are the works of data link layer, okay? So, but we will start in the previous slides, okay, or previous videos, okay, about flow control and error control. And we talked about go back and say keep repeat, something like that. They are the concepts, okay, of data link layers, okay. But what we are doing in this slide is the actual protocols, okay, how we apply those ideas into the actual protocols to read the bit sequence and understand them, okay. So in the previous slide, we talked about flow control, error control, A send to B, and B just send like acknowledgement back to A, right? But for this, we emphasize that A can send to B, data to B, and B also have data to send to A. This is more a normal condition, okay? That A have data to B and B also have data to A. So it's two-way communications. We have three station types: primary, secondary, and combined. Combined means that all stations, like the sender and receiver, they are the same. They are both primary and secondary, okay? The difference between the primary and secondary station is like in the past when the computer were like very expensive, okay? We will have like server that is have like computational, power, okay? And then we have terminals. Terminal is like secondary station that cannot do many things, okay? Just cheap terminal for the for like the people to use, okay? But the computation or like the big calculating or something will be at the server, okay? So we have like primary and secondary like that. But at this moment, okay, nowadays, the computer is much cheaper, so we can use like more like the combined station, okay, which means that sender and receiver, they are both they are the same, okay, and we leave like applications and many things, right, and storage to clouds, right, nowadays. Okay, now the link configuration, we can have unbalanced, which mean one primary and more than one secondary station, or you can have two combined station, which is a balanced configuration. Okay, for the data transfer mode, okay, we have normal response mode. It was normal at that time, okay, because we have like one server as a primary and many secondary, right? This is unbalanced configuration. Secondary can transmit only in response of the primary, okay, but this is probably more a case now, which is the asynchronous balance mode, okay, which means that this balance configuration and the combined station on the other side can initiate transmission. And the third one is asynchronous response modes, okay, which is unbalanced, but secondary may initiate. But we probably gonna focus on the balance configuration, okay. In this slide, I have to tell you that many details, okay, but it's not difficult, okay. So I may go like quite fast, and you can kind of catch up or okay, watch it again, something like that, okay. Look at the HDLC frame structure, okay. When we send as bit like this, Okay, how can we know what this is, right? So we have to identify. Okay, so we identify with a flag. Okay, flag is like when you have a start of a race, car racing or running, as a race, then you have like people who, have a, take the flag, show the flag, okay, that this is the start, okay, starting time, something like that. Okay, so we have the flag as the starting and the end. Okay, then we have address field, we have control field. Okay, information field at FCS, the FCS is error correcting code, okay, which I will talk about. But we have go into detail before on about the coding, error correcting code, okay, but this is error detection. Okay, for HDLC, okay. You can see that flag has 8 bits, okay, it have a unique pattern of 0 and then 6, 1 and then 0. It's shown at the beginning and at the end of a frame, okay. We have variable size frame, okay. Information is variable, so we don't know the length of the frame beforehand, okay. So we have to look at the flag. If you see the flag, this is the end. If you see the flag, this is the start, okay. If you have other protocol that use fixed size frame, you have no need for flag, okay. So they have like other protocol that is called like ATM, asynchronous transfer mode, which we are not talking about here. That's why I'm not writing, but it's fixed size. If you have fixed size, so it's the same size all the time, right? So you can count the number of bytes, and then you know that this is the end of the frame. It's like the same size box, okay? So you can know that this is the first frame, the second frame, third frame, something like that, okay? So then you don't have the flag. The weak point is that 1 bit error can merge or divide the frames, okay? So look at it like this. If you have okay, so this is a flag, right? But if this is wrong and you look like this, so you think this is not a flag anymore, right? So when you are looking for the flag, okay, so you have like flag here, and then this is the first and this is the second frame, right? But then something is wrong like this. So what happened is that it will merge. So you have flags here, and this is not a flag anymore because something is wrong, right? You don't know. So this become merged. Okay, become 1 frame instead of 2 frames. Okay, so this is a problem. Okay, another problem is that in the information field, the data can be anything, right? User can send anything. So the flag pattern can accidentally appear in the information field, okay? So what you do is that you do the bit stuffing to prevent this pattern to happen, okay? So insert an extra 0 after 5 consecutive ones, okay? So at the receiver, if you have 5 ones, okay, then if the 6th one is 0, you will delete it because this is the bit stuffing. This is not the actual data. This is the bit that you insert, okay, to prevent the flag to accidentally happen, okay? But if the 6th bit is 1, 7th bit is 0, then you accept this as a flag. See in examples, okay? If the original is this one, after bit stuffing, you get this, okay? At the receiver, you will just take this out because this is after 5-1, you take the flag, you take the 0 out. After 5-1, you take the 0 out, something like that. Okay. Now address field. Address field is 8-bit and extendable. What does this mean? They want it to be flexible, okay? This is again the very first popular protocols, okay, for data link layer. Okay, you can see that the new protocols like internet protocol, like IP protocol, okay, they are not using the variable size like extendable anymore. They fix the address field, something like that, okay, so it's easier to handle. But anyway, for the idea of the extendable address, okay, you can use the first, okay, it's usually 8-bit long, okay, 7-bit are used for actual addressing, but the leftmost bit, okay, of each octet mean byte, okay, this is the same as byte, is used to determine if this is the last byte of the extended frame or not. Should be extended field, sorry, extended field or not. Okay, so if 0 is not the last byte of the address field, but if it's 1 is the last byte of the address field. So how to see this? So this is 0, okay, so not the last byte. This is 0, not the last byte. This is 1, so this is the end. So it's the last byte of address field, okay? And the whole thing here is in the address field, okay? So it can be 1 byte, 2 byte, 3 byte, something like that, okay? And if you want to broadcast all stations, you use the address of all ones, okay? This means that you are broadcasting. Okay, so we have the flag here and the address already. Next is the control field, which is have quite a bit of details, okay? In the control fields, okay, we have three types. We have three types of frames in the HDLC protocol, okay? In control field, we can identify the type, okay? Information frame, supervisory frame, and a number frame, okay? We call it I frame, S frame, and U frame. Okay. When you want to identify the type of the frame, okay, you look at the first bit. If the first bit of the control field, okay, is 0, then it's I frame, okay? But if the first bit is 1, then you look at the second bit. If it's 1, 0, it's S frame. If it's 1, 1, it's U frame. Okay, so this is how you separate or differentiate between the type of the frames in the HDLC protocols, okay? Looking at the control field. Now, NS is the sense sequence number. Okay, you can see that we also have I frame here and S frame here. This is the 16-bit. Okay, so you have 8-bit control and 16-bit control. Okay, the difference is the size of NS. NS is the sense sequence number. If you remember, sequence number is used for windowing, right? The size of the window, sliding window protocol. So this one you use 3-bit sequence number. Okay, so use 3-bit here. This is also 3-bit sequence number. Okay, NS is the send sequence number, NR is the receive sequence number. So basically, this is the frame number. Frame number 0, frame number 1. This is the acknowledgement. Acknowledgement number. Okay. Okay. So we will look at it in examples. Okay. Maybe in the next slide. Okay. S is the supervisory function bits. Okay. We have 2 bits here. M is a number function bit. We will look at the supervisory function bit in details. Okay. As it fit exactly with the go back executive repeat we have talked before, but we will not go into detail for the unnumbered. You can take a look at it, searching, HDLC protocols, okay, by yourself if you want. This is the receive sequence number, the pole and final bit, okay, we will talk about in a little bit. Okay, this is 7-bit sequence number. And for the supervisory, this is also 7-bit, but this one is just padding 0, okay, padding, no meaning, okay, just pad to make it full. Okay, I have talked about this. iframe will carry data with the AIQ piggyback. In the past slides, okay, we have like A, B, and then you send okay, you send frame, right? and then you have like acknowledgement, okay? But if you want to piggyback, the acknowledgement is like this. You have A, B, receive, transmit, you have A want to send to B, okay? And it's happened that B also have data to send to A. So instead of separate the frame, okay, instead of separate the ACK and the data, it will have the acknowledgement inside of the frame. So this is called piggybacking, okay? If you look at, go back a little bit, okay, you can see that this is the flag and then address, okay, and this is the control, and this is the information, okay? So the whole frame from B to A have like this field, right? So you have ARQ inside, which is the NR. This is to acknowledge, okay? Inside the control field, okay? And then, so this is information, something like that. So this is called piggybacking. The supervisory frame is used for flow and error control. So you act when there is no data to send, okay? So in the supervisory frame, you don't have data to send. Just send just normal, like, so this is like X frame, okay? And then you have a number is for supplement link control functions, which means that you want to set the mode, initialize the transmission, disconnect the transmission, something like that, which is not data transfer, okay? And you also do the pole final. Okay, there are 4 types of S frame, okay? 0, 0, 0, 1, 1, 0, 1, 1, because we have 2 bits, right? If you remember in the S supervisory function bits, there are 2 bits, okay? If it's 0, 0, it means receive ready. This is like ACK. Like if you ACK 5, it means that you have received positive acknowledgement, okay? So you receive the frame correctly up to frame number 4 and is expecting you want to receive frame number 5 back for the next one, okay? So this is ACK 5. So what is reject? If you reject 4, for example, it means that you didn't receive frame number 4, you want to get frame number 4, okay? This is negative acknowledgement in go back N. 1, 0 is receive not ready, okay? This is positive acknowledgement, but you tell the transmitter that you are not ready to receive the new frame. So if you INR 4, it means that you have received correctly up to frame number 4, but you are not ready, you have received correctly up to frame number 3, but you are not ready to get frame number 4, something like that. Okay, 1, 1 is selective reject, okay? This negative acknowledgement for selective reject or selective repeat ARQ. We will have examples of operations in the next slide. Next video, okay? The pole and final bit, what is this, okay? This is when you have command and response, okay? Like in the primary and secondary, or even if it's combined frame, okay? The one side can ask for status of the other side. Suppose A want to know status of B, A can send a frame with pole set to 1, means that it's polling a response. What is your status right now? Are you ready to receive new frames at this moment? Something like that, okay? And then B can answer by setting this bit, pole final bit to 1, okay? Means that it is respond to the command or the questioning for the polling of A, okay? So if, like, for example, timeout, A send frames to B and then nothing back, okay, until timeout, and they may ask for polling, okay, to ask for status, and B may send back, I have received like maybe at 5, I have received correct up to 4 and waiting for number 5. This is my status, and I also set the final bit to 1, okay, something like that. Okay, now information field and frame sequence. If you remember in the frame structure, this So we have information field here and FCS here, okay, which is variables. Okay, FCS is 16 or 32. The normal one is 16 bits. Okay, this is the parity bits. Okay, for the error detection code. Okay, so the information field we apply only in iframe, okay, and maybe some uframe which we are not focused on. Variable length, okay, but must be multiple of 8 bits, must be multiple of bytes, okay. For the frame sequence, this is error detecting code. You calculate from the remaining bits of the frame except the flags, okay. So you have flag here, and you have address, you have control, you have information, you have frame check sequence, and you have flag. So you use all this as data to encode, and this is parity. If you remember the error correcting code, error detection code, okay, you will have data, right? You have data coming in and then you encode, right? You encode and then you get code word. You get code word, you send code word to channel, you receive sequence, and then you decode, okay? You decode by, if error detection, you decode by find remainder of G over divided by G, okay, equal to 0 or not, and then you say that this one is wrong or correct, okay. Okay, and the normal code for the error detection here for HDLC is 16-bit CRC CCITT. This is the name of the code you can search, okay. What is GX, okay. CRC is a cyclic code, which is basically the code that we are talking about, but this GX has 16-bit parity check, okay, which is more than what we are using. So this is the end of the slide. Thank you very much. We will look at examples, okay, of HDLC in the next video. Thank you.